All right, welcome back, everybody, for the afternoon session of today's day, focusing on benchmarking characterization. It's my great pleasure to have the next speaker, Jens Eisert from Freie University Berlin, speaking about the limitations of quantum computing.
That's right. So thanks so very much for the kind invitation to this wonderful place and this exciting workshop on topics that are close to my heart. So this picture kind of gives away what this talk will be about, although this may look unnecessarily drastic and dramatic. In fact, I take a rather positive stance on the development of quantum computing in recent years. That said, on the specific demand of Bill, for the big chunk of this talk, I will be talking about fundamental limitations that one might encounter when thinking about near-term quantum computing in the absence of error correction and fault tolerance, as we know so nicely heard it yesterday. So one of the reasons we are here, I suppose, is that quantum computers not only promise advantages in computational tasks, but this promise seems to be moving closer and closer to reality, creating a lot of interest in the field, mostly for good reasons. So the machines we have today are still rather noisy and they're not huge, but then to think of like 1,000 qubit quantum devices with reasonable average gate fidelities seemed completely inconceivable not very long ago, creating an interesting state of affairs. Now, the elephant in the room, however, on the positive side of things, is whether we can reasonably hope realistic, noisy quantum devices to provide a speed up over classical computers. Now, for paradigmatic problems, there seems to be a case that this may well be within our reach. There's some simple problems. Actually, the simplest of all paradigmatic problems are ones where you go into the lab, not me, never let the theorist into the lab, go to somebody else's lab and you take raw data, which is a sampling experiment, and then there's some experiments of this type that produce distributions that are pretty flat and pretty boring, but that have tails that are so intricate that you cannot sample from a distribution nearby, or sampling up to a constant error in the total variation distance is classically hard. That's interesting, and this can be done, and famously has been done by a number of big players, like for a huge interest in the field, as we know. Well, there's a lot to say about this, even in the absence of errors in the clean case. There's lots of fine print. Dominic, who might be here, and myself put out a review article not so long ago on the fine print of these sampling experiments. Say one cannot black box verify them based on data alone. So what one commonly does to build trust in the functioning of these devices is like to do linear cross-entropy benchmarking that is sample efficient but computationally inefficient. If one has trust in the functioning of the quantum apparatus, one can even go into the lab and take measurements and verify the correctness of the sampling experiment, even though one cannot predict the samples that come out. One has to do the sampling, but one can take measurements and say, what I'm doing is correct, which is an interesting state of affairs. That's very nice. It's very encouraging in a way, but what next? It's not really an application. It just sharpens the mind what a quantum advantage could possibly be. And the answer of what next depends to an extent on who you ask. And for the purpose of this talk, this means that we will, on the good side, meditate a little bit on what applications in machine learning and a bit on optimization we can possibly think of. That's the good part. I keep this somewhat superficial. I will go over this on a kind of high level. As for the big chunk of the talk, we will go to the bad and the ugly, if you want, and think about what limitations may arise if we do not have the type of error correction that these people have talked about yesterday. In particular, we have seen that for, say, depolarizing noise, if you have deep circuits, that pretty quickly you will be driven to the maximally mixed state. Also at log depth, you end up in the Gibbs in an efficiently classically samplable region, so that the quantum advantage presumably goes away. Also for sampling experiments, it has been seen that if you have a constant error per gate, then again you can efficiently sample from circuits of that type, even classically. So in this part, we will have a look at obstructions, how to break it, so against learning, against error mitigation, and for doing interesting stuff for non-unital noise, also following up on nice work by Bill on this subject. So that's the plan, and in the end, we have a bit of a meditation on a showdown between the good, the bad, and the ugly, and we will see who will win in the end, or well, whether anybody wins. So you can judge for yourself. Good. So machine learning has surely changed the world we live in. It's very difficult to deny this. Basically, any algorithm that makes predictions based on past training data in one way or the other has to do with machine learning. And given that machine learning is basically absolutely everywhere, and that quantum algorithms may help assisting for specific structured problems in a way, it makes a lot of sense to think in what way we can think of quantum-assisted machine learning. This can mean many things. So in the perfect world, we would like to have a rigorous guarantee for state-of-the-art learning algorithms that are applied on real-world data sets, so pictures of cats and dogs or numbers, applied to an algorithm like stochastic gradient descent on a model, say, parameterized quantum circuits. And then in that setting, one would want the quantum machine to somehow do better than the classical one. You want an advantage of a kind. This again can mean many things. It can mean that you take fewer samples, fewer pictures of cats and dogs, and learn what a cat looks like. That would be an advantage in sample complexity. You can be faster, an advantage in computational complexity, or in generalization bounds for unseen data. So is there a quantum advantage of a type? And that's something we've thought quite deeply over the last months and years. In particular, we've seen that there is an advantage in Pak distribution learning. That's true both in the generator sense, where one takes samples from a family of distributions, and the learner meditates about them and has to kind of spit out new samples from a distribution that is nearby, or learn the actual probabilities themselves in density modeling. And for both of these kinds, there is an advantage in the specific Pak learning setting. So that's just the fine print of the same thing, that for the family of distributions at every epsilon delta, given access to just the sample oracle, so classical data, one outputs in a time that's polynomial or the parameters with probability at least 1 minus delta. So probably a generator that is nearby in a precise sense, so it's a kind of approximately correct. You take data, you think, and you spit out new data of pictures of cats and dogs. So the proof here goes via so-called Goldreich-Goldwasser-Mikhalich reconstructions using one-way functions to produce pseudo-random functions to give rise to hard-to-learn distributions. But the quantum algorithm can kind of walk this tree backwards and crack to the hard-to-learn distributions. And so the quantum computer can learn efficiently, whereas the classical computer cannot. That's nice, or that's good to see. It's a super polynomial advantage for a meaningful learning task. But the way it's set up, it's like a bit of a crazy type of data. They are reverse engineered. They're surely artificial, and they require a fault-tolerant quantum computer at the end of the day. If you want realistic data, there's also something one can do about that. In particular, not for quantum networks, but for large-scale, sparse-pruned classical networks, we've looked in what way one can use variants of HHL to better train classical networks over families of classical stochastic gradient descent, again, having a superpolynomial advantage in a way. And that's interesting in that it really applies to real-world data sets. We actually have even applied this to the CIFAR 100 data set. That's one of these industrial standards for machine learning, including pictures of cats and dogs for that matter, with a good performance concerning the requirements for the theorem here. So that's good. Again, it uses a fault-tolerant quantum computer, but that's a setting where like natural data would come. So it works for classical data. That's some picture. Yeah.
I was wondering, I mean, I was assumed an obstacle was the classical data has to be kind of read in to the quantum.
Very good. I take like short answers and then I have like the big discussion at the end. The short answers, we have this kind of 5 pages letter and like 60 pages of monstrous appendices. We look at that, so we don't need a QRAM to upload this. So we looked at the point that it's kind of sparse enough so that the uploading is efficient without like funny like QRAM access or something, but not that you cannot do it classically. So this is something we look at in the appendix in quite some. That's a good point.
So the answer is it's okay in the end?
It's okay. You can do it.
It's efficient and you know it's
Just very quick question. In class target training, you mean without the time long, or what is the advantage of
It's a time. It's a computational complexity advantage. Just like in the previous setting, this computation advantage. So this picture is actually not from the data set. It's my own cat. So actually, I developed the habit of getting up in the morning at 4 and having my computer up and my coffee. And the cat also gets up and sits on the computer to work and even puts its claw into the coffee and has some coffee, because the cat thinks that's how you do it in our household. Good. So we also thought about like short circuit learning advantages. This is something that is not out yet, based on these unconditional advantages for sampling, where we thought in a certain precise sense, you can think of concept classes so that you have an advantage of a constant depth quantum circuit over families, meaningful families of log depth classical circuits, which is nice because that is a meaningful separation. It's now for a near-term quantum computer, it's a constant depth circuit, but again for pretty crazy artificial data because it's just conceptually set up. We also looked at the question what way one can think of having quantum advantages in like optimization problems like integer programming, where we looked at kind of also Mario Szegedy looked at this, where we like kind of found a new reduction using Occam's razor and computational learning theory to kind of say in what way there's instances of integer programming that can be well approximated on a quantum computer, but that cannot be well approximated on a classical computer. So this is a good solid work. It's not the end of the story, but it tells us that there's some evidence that in the realm of practical problems in learning, and also to an extent in optimization, there's proven quantum advantages and interesting problems that are kind of encouraging to think further and to give these problems a bit of a practical feel of a kind. So there are proven advantages of a kind, even though this may not be the end of the story. But it's good solid progress in a healthy direction. Which brings me to the bad part. But was there a question in the back? Yep. To the bad part on what limitations we might see. So yes, there are in principle advantages in meaningful learning tasks. That's good to see those. So the field exists. That's already good news in a way. But say when you think of variational machine learning, what people usually have in mind are like quantum circuits, variational quantum circuits that sit there in the center, and you have a bigger classical algorithm surrounding them with control parameters, and then you would kind of vary these control parameters to set up the problem. But for like natural data is not so easy to capture mathematically precisely, and these algorithms, like variational algorithms or GANs and so on, are not so easy to capture mathematically precisely. So you need a bit of a vehicle or so to make progress here. And what seems quite natural is to think in this context of the quantum part itself in the center and ask to what extent, like seeing this as part of a bigger algorithm, one can even learn the output distribution of a quantum circuit. There's a quantum circuit, and you measure it at the end of the day. That gives rise to a distribution. And you ask, can you learn this distribution as a kind of proxy for meaningful learning problems that involve a quantum circuit in the center? So can one learn the output distribution of quantum circuits? And given that this follows the Born rule, these machines are sometimes called Born machines. And so can you? And this has been a bit of a manic depressive phase with ups and downs and kind of funny insights and properties and revelations. So in particular, say if standard secure pseudorandom functions exist, so under a plausible assumption, then already at depth that's a bit deeper than linear, it happens that the learning of the output distribution is hard, both in the generative sense, where one takes samples and wants to spit out new samples, and the density modeling sense, where you want to learn the actual probabilities of the setting. And this interestingly holds true both for quantum and for classical algorithms, which is kind of funny if we think about this, because it means that not even a quantum computer can learn the output distribution of a quantum computer. Well, that's where it is. And that happens pretty early on, like at constant depth, you have the property, a bit more than constant depth, that the learning of the output distribution is hard. It also means that there cannot be a quantum advantage, but it's also rather an obstacle than anything else in that context. That is what you have here. This is for the sample oracle, where you just take data that you can like write on a sheet of paper, just taking the raw data from the experiment itself. What is commonly also studied in this context is the so-called statistical query oracle, which is an oracle that's kind of promised to deliver values that are up to a finite error away from the expectation value. It's very common in these algorithms. You would kind of apply parameter shift rules, whatnot, and then estimate expectation values at the end of the day. So how can you learn the output distribution of circuits with statistical query oracles? And here it turns out that even at logarithmic depth, you can't learn the output distribution. Well, that's kind of interesting. And again, well, this is like also for generic learning algorithms. At log depth with SQ oracles, you cannot learn the output distribution of circuits of this type. Which is kind of funny if we think about this, because it these circuits, in particular in one spatial dimension, are obviously classically efficiently simulatable. Right? If you have a log depth circuit, you can efficiently simulate that circuit both in the weak and in the strong sense. So without wait a minute. So how are actually simulation and learnability related? And this goes very crisscrossy in the literature. You read that things can be simulated, they can be learned. If they can be learned, they can be simulated. And I mean, your head explodes, or my head explodes. I mean, maybe not your head. But there's a bit of I think it seems fair to say that there's a bit of an element of confusion how these things are precisely related. So we thought, is there a connection? And of course, in the context of classical simulation, how can you not think of the mother, father, diverse of all efficiently simulatable circuits, which are Clifford circuits, which are clearly efficiently simulatable, both in the strong and the weak sense. Can you learn the output distribution of Clifford circuits? And here the answer is so how are simulation and learning related? And the answer is for Clifford circuits, you can learn them actually efficiently. Yeah, and that's actually less true than you might think, because I mean there's still many Clifford circuits, obviously. It's not such a small concept class, but the Clifford circuit output distributions are uniform over a fine subspace of the finite n-dimensional vector space, and then one can formulate a kind of finite field Gaussian elimination problem to actually learn the distribution. Good. So Clifford circuits can be learned efficiently. Now we know that we learned yesterday from Stephen's nice talk and from others that the bread and butter in error correction is to think of Clifford circuits, transversal in that context, and adding the expensive T-gates from magic state distillation, whatnot. So the T-gate are the expensive resource, and you have the Clifford circuits that are cheap. So you can say, well, you uplift Clifford circuits to universal circuits with adding T-gates. How many T-gates do you need to add to end up in a hard-to-learn distribution? So you take the T-gate, here it is, and you place it in the circuit. And it turns out that this one T-gate makes the learning hard. That's kind of funny when you think about this. This is the proof goes by a parity learning with noise problem. Is kind of interesting when you think about this. Obviously, the simulation is still efficiently possible. That would be true up to logarithmically many T-gates, both in the weak and the strong sense, clearly, but you can't go back. Once you have a distribution, you cannot learn the distribution anymore with a single T-gate, even though the simulation is perfectly and classically efficiently simulated, which is kind of funny. That's actually even true in the average case sense. There's a follow-up that came out not so long ago that also in a precise sense, it's an average case hard. So, so the connection between simulation and learning is intricate, maybe more intricate than one could have thought. It can be seen as an obstruction to proving quantum advantages if one sees these guys, these Born machines, as proxies in variational algorithms that are surrounded by larger algorithms. But above all, these are first rigorous insights into the learnability of outputs of quantum circuits in a way that's kind of clarifying what's going on. So we were by no means the first ones to ask these questions. There's a wonderful paper by friends in Edinburgh that had a paper on this that, to be fair, didn't have many results, not many theorems. I say this with all respect, but they posed very many interesting questions. So we followed up on this, and this paper had this kind of cute title because it was talking about quantum supremacy, and Born machines had the cute title of the Born supremacy. But then we sat down and worked hard to find out what the identity of these advantages is, and thought, now we have the identity of these Born machines, so we should call our paper the Born identity. But this I didn't get across my co-author, so we had a very technical title in the end. Yes?
Why is hardness of learning an obstruction to quantum advantage?
Okay, it's not really directly an obstruction, but well, it's kind of a proxy for seeing quantum algorithms as part of a variational circuit. So we would think that the quantum part should be efficiently doable so that you can learn the distribution, so that you can get actionable advice on how you change your control parameters. It's not an actual obstruction. I come to actual obstructions, but it has a bit of a negative feel to it. So it's a mathematical question that's inspired by looking obstructions against quantum machine learning. In fact, we have this short circuit separation. So for some short circuits, there are learning problems where you can do better quantumly than classically. So that's good. So that's for the noiseless case. But actually, circuits are noisy. That's, of course, the core problem in all of this. We wish to have noiseless circuits. So what do we do about this? Well, the entire day was dedicated to quantum error correction yesterday, and that's a topic that's hugely exciting also to me, but I'm not talking about this today. I'm sticking to my theme. Also not all benchmarking, that's also interesting, but I'm not talking about that either. What one commonly does, but the problem is, as we have also learned yesterday, is that while you can accept certain noise levels, which are finite, the known schemes for fault tolerance come along with substantial overheads, and maybe prohibitive overheads, to the extent as we know that we like saw spectacular numbers in some of the talks yesterday that were like somewhat demoralizing, if you want. So what people commonly say is, like, I mean, it's good to aim high, but along the way, what we should do, and that's a good advice, is to do the best with the data we have and take our circuits, which are noisy, take data and take samples of them, and then try to undo as much of the noise as we can based on classical data and classical post-processing. That's what it is, because the circuits we have are not like that, but they are circuits, and estimate stuff at the end or take samples in the sampling experiment I mentioned. But this is not how things look like. If you open the hood, you find circuits that are noisy, and one of the plain vanilla schemes of these circuits, like the Volkswagen of the schemes. Well, actually, I recently gave a talk and I was mentioning the Volkswagen of the air noise models, and somebody else spoke after me and on error correction, and was giving a talk on a collaboration with a car maker, and said he's talking about the toric code of the car makers. Anyway, so you have the perfect circuits followed by noise, and that's a common model that is like, that's not quite what it's in reality, but it's not such a bad model. And in the most plain vanilla of these models, you would have, say, the perfect circuit followed by depolarizing noise that's characterized by a depolarizing noise parameter, but this can also be non-unital, so that the entropy may also be increasing in the process. So error mitigation is not one protocol. It's more like a family of protocols. It's a mindset, if you want. You take data and you want to undo things. There's a couple of very well-known schemes of that type. And one of the most well-known most used ones, it seems fair to say, is zero noise extrapolation, where one accepts that it's much easier to add noise than to decrease it. So you would add certain noise levels in a very controlled fashion, and then you would extrapolate to the zero level and then extrapolate to zero error given the data that you have. That's very nice. There's a lot to say about this, and it's also, I think, in the heart of the IBM strategy to think of error mitigation in this sense. And this is a good idea. It's a wonderful idea. It can be done. It should be done. It is done. It's all a good thing to think in these terms. One should take data and error mitigate along these ways. This is, we hear more about this. In fact, I think Christian will speak just after me, and I'm sure he has wonderful results to report. What we were thinking about at this point was, like, are there limitations of that? Like fundamental limitations, asking, it's a great idea, you should do it, but how far does this go? And for this, we formulated like a mathematical abstraction of having these circuits, which are noisy, that produce outputs, and then you have these classical outputs, and there's a classical algorithm that takes all these outputs, and this algorithm is aimed at producing expectation values of observables or samples at the end of the day, given the collection of classical data. And this is aimed at reducing the noise levels in a way. So the flavor already is that of a statistical inference problem, the way we formulated this. That's in terms of the circuit depth, d, the number of layers of gates, the circuit width, n, and the depolarizing noise strength, p, that kind of governs how noisy the circuit is at the end of the day. And we want to have a sample complexity bound asking how many copies of this noisy state that comes from the noisy circuit are needed to estimate the noiseless expectation values for a given family of observables to a precision epsilon and probability 1 minus delta inspired by a PAC reading of this kind. And here are our results. Two theorems for like depolarizing noise. You need p to the power of something that goes like n times d for mitigating depolarizing noise. For d is like of the order log n. And this happens at log depth. There's the mathematician's joke that log is upper bounded by 4. And that's not such a bad joke if you think about this. You need a big n to arrive at 4, if you think about it. And for mitigating non-unital noise, there's a c that can be given that, again, has this n times d behavior. Why is that interesting? Well, one needs of the order e to the power n times d many samples for mitigation. And what was previously thought it was like e to the power of d, but it's d times n, like the system size. And since in the NISQ regime, one expects d to be of the order log, our results are exponentially stronger than what was previously known. And that's really a challenge for variational quantum algorithms, in that already at log depth, error mitigation in this sense is actually challenged for a large family of practical schemes of the type, at least as an asymptotic statement. So how does the argument go? I have no time to go into the details of the proof, and I will not overrun. I kept the promise to the chairman. On the highest level, the point is to set up a learning problem that can be solved by error mitigation, so that if one had solved the error mitigation problem, one would have solved the learning problem. And basically, one sets up a problem where one feeds in computational basis states or the maximally mixed state. One wants to see, one wants to discriminate the maximally mixed state from the computational basis at the end of the day after the noisy quantum circuits and the error mitigation schemes of a kind. And this has the flavor of a kind of multi-hypothesis testing problem where we use a variant of Fano's lemma. That's a single sample test that distinguishes the n+1 distributions from the computational basis state and the maximally mixed state. That it's an expression that involves lots of relative entropies. And that's applied to the noisy state distinguisher for computational basis states or the maximally mixed input there where one can bound the right-hand side. And that's it's a small step here. It's pages and pages in our paper, but one can bound the right-hand side in the right fashion and get the right scaling. So this e to the power of n times d scaling on the right-hand side after blood, sweat, and tears. But this is what you get. So this is what it is, but then you have to kind of sit down and construct circuits for which this bound that involves these relative entropies is actually large. It's huge. And for this, and this is like where the worst case flavor of the argument comes in, one has to look at circuits that are very mixing, very scrambling. In a way, this was mentioned so many times already today. You need to have random circuits that are mixing, and it turns out that it's good enough to look at certain purities of the output. So the purities must be small, which ask for having certain epsilon approximate 2 designs in the circuit. It is known that certain Clifford circuits with long-ranged interactions give rise to epsilon approximate 2 designs in polylog in n depth, and this can be put together. And one sees that these kind of random circuits shift the purity contribution to larger weight Pauli words. And that's important because the depolarizing noise acts drastically. It acts exponentially in the Pauli weight. And the more you have Pauli weights, the more drastic the depolarizing noise acts. But this means that this applies to circuits that would be epsilon approximate 2 designs and would be very mixing in a way. And this is where the worst case flavor of the argument comes in. So it doesn't mean that error mitigation does not work, but there is other strong obstructions against error mitigation already at log depth. I made my point. It's kind of basically constant. It's a finger snippet more than constant depth as an asymptotic statement. It does not constrain quantum error correction at all. No, it doesn't. So maybe that's a good way to strive forward. It also invites new intermediate schemes outside the box. And there's a couple of schemes that don't quite fall into the category that we have mentioned here. I mentioned one of the papers of us that does a kind of mixture of randomized benchmarking and robust shadows. That's the one thing I say about benchmarking today, but it follows up on what Joe has said earlier today. That's a bit outside the box that may not fall into that category. But it's an invitation to think harder about mitigation schemes that would not fall into the category. It does not mean that error mitigation does not work. One should do it, but the way it's done, it just does not scale basically at all. And it does not work well for all circuits. It may work well for some circuits. It also means that noise and very non-local circuits don't go together well. If you want to spread noise all over the place, it's bad. But maybe if you keep things at bay in very local connections, it's okay. But then you also have not very much expressivity. So there might be a sweet spot in the middle. I don't know, but see it as an invitation to look for the sweet spots in the middle. So in fact, that's my last point, 34 minutes into the talk. Motivated by this, we looked a little bit more into the impact of non-unital noise. In fact, this turns out to be more drastic than anticipated. And that also follows up on nice work that Bill and collaborators have done, and also overlapping authors with our team, in that depolarizing noise and non-unital noise acts quite differently in that depolarizing noise scrambles the information. All it does, it drives systems to maximally mixed states, and they sit there, whereas amplitude damping, as the most paradigmatic of non-unital noise channels, removes entropy. You get a pure state out that also loses information, but at least you have a pure state with low entropy. And there's this beautiful proposal of the quantum refrigerator that kind of makes the point that under certain well-devised readings of non-unital noise, you can do a very long computation, because you can basically use this refrigeration, this amplitude damping, as a way to generate clean qubits that you can then use in error correction in later steps. It's a beautiful proposal already from some time ago. Good. So this was a kind of invitation for us to sit down and see what we can say about non-unital noise. And this was a small thing. It became longer and longer. It became a 60 pages monster in the end. This came out not so long ago, quite recently. So what we found is that if you have a deep random circuit under any uncorrelated, possibly non-unital noise, the circuit becomes effectively truncated in the sense that only the last log-n layers of the circuit matter, and exponentially quickly from the end of the circuit, the impact of earlier gates is exponentially suppressed till the end. So it's kind of a thin layer at the end that matters, and the previous stuff is gone. So the influence of gates on Pauli expectation values at the very end decreases exponentially the way you go away with from the last bit in the circuit. There's also a lack of barren plateaus, which is kind of curious. I mean, you know that one of the most familiar algorithms in this field are variation quantum algorithms, where you have your control parameters, you have a cost function that's given by, say, a fictitious Hamiltonian, and you want to vary the parameters kind of to minimize the cost landscape in a way. And one of the commonly stated problems, among many other problems, our life as quantum computer science is quite troublesome, but one of the commonly stated problems is that the cost function tends to be very flat. Gradients are exponentially small, and also the variance becomes very small. So that means you vary, but if you want to estimate gradients from expectation values, you don't know where to go, and then you're stuck and you cannot vary them. They're untrainable. So here, interestingly, we had a bit of a manic depressive phase saying that, yes, you don't have barren plateaus. In fact, the cost landscape is never flat and the gradient never vanishes under non-unital noise. And it's kind of cute that whenever you're non-unital, that's the property you have. So, interesting, yeah? So for the little bit non-unitality, you have this effect of having no barren plateau. That's the good news, but there's still, I mean, they may even be trainable, but then you have the problem that the last log n layers are trainable, but then you have a little expressivity because they may be trainable. You have a very wobbly cost landscape, very good, but you cannot do much with it because you still have the log n layers. So it's not really good news. It is what it is, but it's kind of cute to see that the effect seems to be drastic in that for non-unital noise, you have a very different effect than for depolarizing noise. We can also, and that's my last theorem, I think, one can also classically simulate on average expectation values of any observable. And this on average is very important. We can't talk about all circuits. And that's also due to the existence of this quantum refrigerator. There are some circuits where you can do much, but on average, we have strong obstructions. And we can also deliver a classical simulation algorithm for any observable to epsilon additive precision with probability 1 minus delta with an effort of this kind. So for constant precision, that's efficient in all dimension. For inverse precision, that's polynomial in 1D. And well, that's what it is.
Is this for the non-unital case?
It's for the non-unital case. That's right. So I give a bit of a hint of the proof. I mean, just superficially. So for depolarized noise, I mean, all the circuits do is they drive systems to the maximally mixed state, and they do so in log depth, basically. For non-unital noise, there's not this one proxy state they are driven to. Yeah, I mean, there's not an immediate analog of the maximally mixed state. They would go to different states, but in expectation, and that's necessary, you need to think of averages, one sees that the outputs of different states are coming closer in one norm. And what we technically do is we look at in expectation over circuits, look at certain Pauli expectation values, and then upper bound this on the right-hand side. And this also gives rise to a simulation method when one accepts that one can kind of truncate the circuits up to log depth and then estimate these in expectation Pauli expectation values and then put it together to use this log depth truncation and to get an estimation method for estimating expectation values of Paulis at the last layer. Good. So non-unital noise acts strikingly differently. It's very different from unitary noise, which is interesting. There's a bit of room for maneuver. It's not really good. Oh, what happened here? Not good news. I mean, you can train it, but you are limited in the expressivity. But it's still interesting to see that the type of noise you have is so important to the statements you can make, and it seems to have a very big impact. That's
your algorithm will work for sampling as well?
We are working on that. So obviously, that's the next question. I have something to say. I mean, that's maybe for after the session. It's a very nice. I mean, of course, I highlight your work that shows that you don't get anti-concentration in the same sense under unitary noise that inspired our work. But on sampling, I have something to say about this, but that's not fully settled yet. It seems fair to say. Good. So we have strong results on average. Again, there are some funny circuits where this is not the case, but on average, we have these very strong results. That's an invitation to look at this. Which brings me to the coda on near-term devices, because I have like 5 minutes left. It's a good moment to slowly come to the conclusion. So in this talk, we asked, or I asked, you had no choice, whether we can hope noisy, realistic quantum devices to provide a speed up over classical computers. And over the journey of my talk, we saw some good things. For example, you've seen that there is super polynomial advantages in PAC learning. It's a bit abstract, yes, but it's good to know the field exists. Yeah, so there's a learning advantage of a kind. But how much structure do we need? That's not so easy. A single T-gate renders learning hard. This can be seen as an obstruction, but at the same time, there are also constant depth advantages on the good side again. The last word hasn't been spoken. I'm not saying that we have solved the problem, but we are doing step-by-step solid work on progressing in the field. I think it's a healthy enterprise. We've seen very strong limitations for against error mitigation already at log depth. It's not saying that error mitigation does not work or should not be done. It should be done. It's just not scalable in the sense in the worst case. It is what it is. It's good to know the limitations of things. It doesn't mean it doesn't work. Also, noise can help. I didn't say about this, but we used ideas of classical machine learning to show that if you add a bit of noise, then sometimes you can provably get away from saddle points, and noise can be a good thing and not necessarily a bad thing. Against the paradigm of noise being our big enemy, of course it's our big enemy, but a bit of noise can be a good thing. As with most good things, they're best consumed in moderation. Symmetry can help. Yeah, well, good. Insights into generalization, expressivity, yes. Gadgets can help. Maybe that's not so important, but what is maybe more important is to think how far this can go and to what extent we can dequantize these things. And at some point we had a heart attack as we thought we had shot down variational machine learning, in that there's a Freie picture of these circuits and you can do like sampling at the end, until we realized that while you can, in instances, evaluate the circuits efficiently and actually sample from it, that this does not necessarily apply to the functional dependence on the knobs and the cost landscape. So the training may not be efficiently doable, which invited us to think more deeply about random Freie features and like notions of dequantization of variation quantum circuits in a way. So this was the more mathsy version of this paper. Also seen that non-unital noise acts very differently. There's an effective depth picture where the last word hasn't been spoken, but it's kind of cute to see that non-unital noise is so different from depolarizing noise. And this is a natural noise model. We have to take this much more seriously than we think. You cannot just talk depolarizing noise and hope for the best. It may be totally misleading to think about these predictions for depolarizing noise. At the end of the day, when we say what is the most near term of applications, maybe I pick up a theme that was just mentioned before the break, which is, who said this? On analog devices, we should not forget that maybe for a good time to think of near-term devices, analog devices, not such an unhealthy thing. So like here's work that we did on analog simulation of curved space-time in a way, judge for yourself. But I think we should become friends with the idea that analog simulation and probing physics questions is not such an interesting scope for near-term quantum devices, in particular when it's equipped with ideas of like Hamiltonian learning, where you take data and learn the Hamiltonian of the system, as we did for our friends with Google, where we learned the Sycamore chip. And once you've learned the Hamiltonian of the system, using like efficiently classical schemes, you can make predictions, quantum predictions, that go beyond the scope of classical simulatability. That gives rise to an interesting state of affairs. You take to time evolution, you learn the Hamiltonian, and then you make predictions that go beyond what you could do classically. And I think that's a healthy way to think about things. So, can we hope noisy, realistic quantum devices to provide a speed up over classical computers? And my ultimate answer to this question is definitely maybe. So, on that note, I thank you for your attention. I'm looking forward to questions you might have.
Thank you very much, Jens, for this very nice talk. Joe?
Your results on zero noise extrapolation,
Yeah.
do you see a way or an obstacle to them extending to probabilistic error cancellation?
Oh, that's included in our setting. That's right.
Oh, that is included.
That is included in our setting. I think the biggest, I mean, of course, okay, that is included, but the broader question of your time and interpreting your question is like, where are the loopholes? What can you do? And again, what we say is worst case. So the circuits we apply may be pretty crazy from a practical perspective. So maybe that's too pessimistic. That's a loophole. Or you do coherent things. I mean, you can do more general coherent things. We have been thinking about using like RB data in your style, and then applying, merging this with robust shadows, and then do estimation of expectation values using RB data. And that's outside our scheme. And that seems to be more robust. In fact, we have theorems of this kind. Yeah. So, but that's unfortunately included. So that's not a loophole.
Yeah, sorry, same topic, a brief question. So your theorem 8, can you go back to that? You got this p to the minus nd.
Yeah. N times d, that's right.
Right, exactly. So that to me, that makes quite a bit of sense, because that's roughly the bound you would have to expect for PEC, or probabilistic error cancellation.
Yeah.
But what I'm wondering now is, so where does this unconditional d log n, or where does that come from? So why is that bound on top? Because I mean, I understand that bound on top, but where does the log n come from? In that, I mean, I could see if I do this nd, that makes sense. That's exactly sort of the volume I get to have.
That's right. But the point is that, I mean, if you just say that exponentially quickly you're driven to the maximum limit state, then you get this e to the power of d in the depth. The point that we have is that there's this n dependence, which makes it different. The n times d makes it hard. And then you see that this means that at n log n depth, you get the obstruction.
Right, but there should probably be some p or epsilon dependent in that omega, right? Is that hiding in the omega?
No.
So suppose I give you a circuit. I give you a device. Some fairy comes along, gives me 3,000 qubits at 10 to the minus 15.
Okay.
Right, and so you're saying even at that rate, I only can do log n.
Yes, that's right.
So I couldn't run Shor's algorithm on a 3,000 qubit device with an error rate of 10 to the minus 15.
Well, that presumably not. No, I mean that depends on the error rate. But I mean, I'm sure you've looked at the numbers. Then no, that's an obstruction against running Shor.
Yeah. All right. Thanks. Just wait a second, please, so everybody can hear you.
So the log n comes from because we constructed certain extremely scrambling circuits that that because what Jens has been saying that this is a worst case result. It's a worst case result because we constructed certain circuits that demonstrate this kind of sample complexity, and like basically those circuits need to scramble before this thing can happen, and the scrambling can only happen at a certain depth. So that's where the depth lower bound comes from.
It's a lower bound on the depth, or only then this bound holds, or what?
Yeah, so the depth has to be greater than log n before like this sample complexity lower bound can kick in.
Okay, gotcha.
No, but it's still. I mean, but that's the point. That I mean, it's worst case, right? I mean, because the way it's constructed, it goes via these two designs, and then you need these very scrambling circuits, and then your circuit might not have that property, right? I mean, that's the point. That it's not. It's a worst case result.
So what you're saying is I have to go log n deep before I basically.
Yes, but it's still. I mean, that's an obstruction because if you are more than log n deep, then you have that result. So
Okay,
that would be. I mean, what you said about Shaw, and that would be applicable. Then.
Yeah. Okay, makes sense. Yeah.
Further questions?
Yeah.
Oh, so in the earlier slide, you said.
So in the earlier slide, you said learning the outputs of log n depth circuit is hard.
Yes. For the SQ oracle, yes. Statistical query oracle, yes.
Maybe I'm not familiar with the task is, but naively I would expect that like doing there should be some efficient tomography method for log n depth circuit, like quantum state representing that, or.
Well, maybe, but the surprise is not. I mean, when you only have expectation values in this sense available, then you cannot like learn the distribution in the sense it cannot produce a generator that takes this data and then would efficiently like sample and computation efficiently spit out new samples from the distribution that you have in the device. So that would be an obstruction. Yeah.
Assuming that P is the error probability,
then in theorem 9 shouldn't it be 1 minus P to this power or something?
So P is like the noise parameter.
So it is very small for small noise.
No, P. No, it's. I mean, okay. Like my P is your 1 minus P.
So it's like fidelity.
Yeah. That's right.
So then in Shor's algorithm, if you have 10 to the minus 15 error, it's like you can do it because P is like 999.
But it depends on what n is and what d is. I mean, we'd have to look at the numbers. Maybe we should do this. Maybe that's a good thing for the next coffee break. We should check actually. That's like interesting.
Right. Okay, if I don't see.
Okay.
You mentioned the coffee break already. Thank you,
exactly.
Jens again.
Thanks for the
and then reconvene at 3:15.